Hello grade 12s, welcome back to another video lesson. So we're going to start by going over the corrections from exercise 40 on page 309. So I hope that you aren't struggling too much with this topic. Okay, of course it requires a lot of writing and you have to be able to interpret the differences between these molecules. So let's have a look. The first one asks you to give the IUPAC names and then to explain the differences in boiling point. So we'll start with that. So this first one, we can see it is a haloalkane with the longest carbon chain being 4. I can see that the chlorine is going to be on carbon 1, which means that the first one here has the IUPAC name of 1-chlorobutane. Okay, then if I look at the second one, I notice it is also an alkane, but now it has the longest carbon chain of 3. So I can see that there is a methyl group that is on the second carbon. So remember, we don't have to give the name if it's on the second, because obviously it can't be anywhere else, but we will give the name for the methyl, for the chlorine. So we'll say 2-chloromethyl propane. Okay, remember it's all one word. Okay, if you said 2-chloro-2-methyl, it's also fine. You can do that. Okay, so now if we notice, the boiling point of the 1-chlorobutane is 78 degrees, and the boiling point of the 2-methyl, the 2-chloromethyl propane is 51 degrees Celsius. Okay, so in order to explain the differences in boiling points, we need to start with that step process that I showed you earlier in the previous video. So you would start by first identifying what type of IMF exists between the molecules. So we'll start by saying that 1-chlorobutane has London forces, right? Because they all have London forces. But because it is a haloalkane, it also contains dipole-dipole forces. Okay, then if we look, 2-chloromethyl propane also has London forces and dipole-dipole forces. So now we ask ourselves, okay, well, they both have the exact same IMF. So obviously they have to differ in another way because they are the same functional group, so they have the same IMF. Okay, so we continue. We say, well, 1-chlorobutane has no side chains. Meaning it has the stronger London forces. Okay, remember we said that as you add side chains, you're going to decrease the strength of IMF. So the one that has the least number of side chains will have stronger London forces than 2-chloromethyl propane. Okay, and then don't forget that you must conclude your little statement to talk about the forces needed to overcome. So you will say the force is stronger let's say the force needed to overcome sorry. So it's the energy. The energy needed to overcome the forces. Overcome the forces is greater in 1-chlorobutane, hence the high boiling point. Okay, so notice that I've done 4 colors to show you the 4 different points that I'm including when I answer this type of question. Okay, let's have a look at number 3. It says to arrange the following compounds in each group according to increasing boiling points and give a reason for your order. Okay, so if we're going to do increasing boiling points, then we're obviously going to also do increasing IMF. That's basically what they're saying. So let's notice that all 3 are going to be haloalkanes, right? Because they have this iodine. So if you see, well, they both have the same functional group, but we notice that they differ in lengths of carbon change, right? If you look, you have CH3 and then CH2 4 times, CH3 CH2 6 times, and CH3 CH2 5 times. So there isn't really a need per se to draw the molecule. Okay, if you want to, you can, but it's actually quite, you can actually see it quite clearly when you look at the formula here. Okay, so we'll start, before I list them in order, we'll start by listing firstly, and you can do this in bullet points as well. It's up to you. I mean, it's easier to do it in bullet points, then you can see each point that you've given. So we'll start by saying that all the molecules have London forces and dipole-dipole forces. Okay, then we'll explain that boiling point increases as the chain length increases. Okay, so the longer chain has a greater surface area of contact and therefore stronger London forces. Okay, so the one that has the greater surface area, stronger London forces, and then we'll do our little conclusion statement to say more energy is needed to overcome these forces. So if we're going to list them in order, we're going to list them, if it's increasing IMF, it's going to have to increase in chain length. So it will first be CH3, CH2, 4I, and then CH3, CH2, 5, and the last one will be CH3 CH2 6I. Okay, so the next one, we notice that the functional groups are changing, right? We can see that the first one here is going to be an alkane. The second one I can see is an alcohol. Then I have an haloalkane. And then the last one I can see is also going to be an alcohol. Okay, so I can see that this one here is pentane. Okay, then I can see the alcohol is 1, 2, 3, 4. So it's going to be butane 1-ol. The last one is 1, 2, 3, 4, 5. So that's pentane 1-ol. And then the haloalkane is just going to be 1, 2, 3, 4. So it will be 1-bromobutane. Okay, so we can start by saying, well, pentane only has weak London forces. So little energy is needed to overcome those forces. Then 1-bromobutane is polar and has London and dipole-dipole. So I'm going to use LF for London. You obviously can't use LF in the test. And dipole-dipole. So then more energy is needed. The alcohols have London forces, dipole-dipole, and hydrogen bonds. So more energy is needed. But there's two alcohols. There's butane 1-ol, pentane 1-ol. So butane 1-ol has the shorter carbon chain, or you can say less surface area than propane 1-ol. So therefore propane 1-ol has the higher boiling point. Okay, so the order, I don't really have enough space to write it, so I'm just going to put the numbers. So the first one in increasing strength, right? They said increasing boiling point. So it will first be the alkane, then the haloalkane, then the butane 1-ol, and then the pentane 1-ol. writing the carbon chain, not the number. Okay, then if we look at 3.3, so I notice that they are all the same functional group, but I see that there is a side chain there. So again, you can draw these molecules out, and then I see that there's a second side chain. There's a side chain here, but I see that there's two of them, which would imply that there's more side chains. Okay, so I'll give you the names for each one. So this one is going to be heptane. Then this one will be 1, 2, 3 methyl hexane. And then this one is going to be 2, 2 dimethyl pentane. Okay, so as number of side chains, as the number of side chains increases, the strength in London forces decreases. Okay, therefore less energy needed to overcome these forces. And then therefore we can see that the order will be the increasing. We'll start with the 2, 2 dimethyl pentane, then 3 methyl hexane, and then the last one will be heptane. Okay, so moving on, 3.4 says ethanol, propane, and then fluoroethane. Okay, so let's start by listing them. So ethanol, right, is a polar molecule with London forces, dipole-dipole forces, and hydrogen bonds. Okay, propane is a non-polar molecule with London forces only. And fluoroethane is a polar molecule with London forces and dipole-dipole. Okay, so we can see that the increasing in strength will start with propane because it has the only London forces, then the fluoroethane because of the dipole-dipole forces, and then lastly the ethanol because of the hydrogen bonds. Okay, then question 4 says the following table shows the boiling points for isomers of C5H12 and C8H18. So it says refer to the intermolecular forces and explain the differences in boiling points between compounds A and compound D. So if I see A is just a regular flat-chained 1, 2, 3, 4, 5, so it's just regular pentane, And I can see D is 1, 2, 3, 4, 5, 6, 7, 8 octane. Okay, so I can see that there's definitely a difference in the longest carbon chain between A and D. So we'll say D has the higher boiling point as it has the greater surface area. So D has the stronger London forces than A. And then you would say the more energy statement, more energy needed to overcome those forces. Okay. Then A and C. So C is this one here. I can see the longest carbon chain is going to be 3. So I have 2,2 dimethyl propane. So I can clearly see that C has more side chains. So if we then look compound A will have the greater surface area. Then C due to side chains. So therefore A has stronger London forces, more energy needed to overcome the forces, therefore A has the higher BP. Okay, then 4.2 says explain the change in boiling points in compounds D, then E, then F. So D is the octane, E is the 2-methyl heptane, and F I can see is the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this one is the, we would number closest to the, well, it's methyl, so I mean it wouldn't really make a difference. So it would be 2, 2, 2, 2, 4 trimethyl pentane. So I can see from D to F the side chains are getting more. So from D to F the surface area decreases as the number of side chains increases. So less surface area means weaker London forces, so therefore the less energy is needed to overcome these forces. So it says explain the change in boiling point, so you must say therefore the boiling point decreases from D to F. Okay, then it says why does symmetry influence the melting point of a compound but not the boiling point of the compound? Okay, so this is not part of the homework. I think I ended at 4. So let's try and answer this question. So when we think about the melting point of the compound, right, we are looking at the temperature at which, so we need to consider, well, remember a melting point is where something exists as a solid and it's going to become a liquid. Whereas boiling point is when something exists as a liquid and is going to become a solid. So when we think about symmetry, we think about how closely packed the molecules are in this crystal lattice. So symmetrical molecules are packed closely in a crystal lattice. So therefore there will be a stronger forces of attraction and more energy needed to overcome these forces. Okay, so we already know that. We already know that, symmetry is influencing the way that the molecule looks, and then we can also then determine the amount of energy needed. Well, we can compare the energy needed to overcome these forces. So this means therefore the melting points are higher because the fact that this compact crystal lattice requires more energy in order to overcome the forces to change from the solid to that liquid phase. Okay, but if we think about liquids are not packed like crystal lattices are. So therefore the symmetry does not affect boiling point. Okay. So I'll go through one or two of them more with you. So if we look, it says, which compound of the next pair has the higher melting point? Support your answer by drawing the structural formula for each compound. So we'll start with this one. I'll call that number 1. So we have C CH3, C, CH3, and CH3. Then we have C, CH3, CH3, and CH3. Okay, please make sure that you take a moment to pause the video and also draw the molecules yourself, because obviously you need to make sure that you practice. Okay, and then the second one will be CH3, and then we have CH2, and that is repeated 3 times. Okay, let me just repeat this. Then we'll do another 2. And then we have CH3, Okay, so take a moment, maybe pause and write down the names as well so that it's just helpful. So we can see that the name for this one will be 2, 2, 3, 3 tetramethyl butane, and I can see that this one is going to be 2 methyl heptane. Okay, so when I compare now these molecules to see which one has the highest melting point, I first notice that they are both alkanes and have the same molecular mass. Okay, but I can see that the 2, 2, 3, 3 tetramethylbutane has more side chains, many more side chains than the 2 methyl heptane. Therefore, molecules are more closely packed, resulting in stronger forces and higher melting points. Okay, so the structures also do help us in order to visualize exactly how this looks and why they will have these differences in their boiling points and melting points. Okay, so I'm going to leave it there for now. Okay, so for your homework, so that you can practice, I'm going to give you the rest of this activity. So it means from number 7 until number 10. Okay, so the corrections, what I'll do is I'll give you the corrections very quickly in the next video, and then we'll move on to the reactions. So please make sure that you are practicing and that you're writing your full statements so that you get into the habit of making sure you don't forget any information. And then, yeah, I hope that it's making sense. And then I will see you on the next one. Bye-bye.